Music theory, the basics of sound and pitch. Remembering our primary objective here is applicable, practical music theory that helps us to actually play our instrument better, for us, that instrument typically being the guitar. However, the same concepts do apply for other instruments as well. We want to learn music theory in such a way that it not only helps us to learn the basics, but is also scalable. In other words, we want to avoid learning rules that only apply to the basics, but aren't actually true once we expand our knowledge and understanding. So to do that, however, we got to dig a little bit into the science of music, which is basically what we're doing here. What is sound? What do the notes actually mean? And I think that is going to be applicable in particular when we think about some of the ideas that we take for granted, that we take a priori when we start to build our worksheets. And we do want to understand and think, hey, what does this mean? How did they come up with this? Two primary examples, for example, are the note names. Why is an A an A? Why is a C a C? What are those things? We're just accepting them a priori. There's 12 notes. I'm just accepting that and then moving forward with the music theory. We'll get a little bit better understanding of what that is here. Also, and this one's a little bit more complex, we just accept a priori in Western music the formula for the major scale that also leads to the construction of the modes, the whole, whole, half, whole, 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 half. Where does that come from? Why do we use that? Now, we might not get to that exactly in this presentation, but we're going to lead into at least some ideas as to why they came up with that scale function or formula as well. All right, so what's the definition of sound? A vibration that travels through a medium, typically air, and is perceived by the ear. So when we think of sound, it's kind of hard to envision sound, and envisioning as human beings is what we typically want to do because we're mainly visual kind of animals here. So that's what we'd like to see. So we envision basically a wave, which you can compare to a water wave, noting that a water wave is traveling through what we call a medium, which of course is the water in that case. The sound is also going through a medium, which is the air. It's harder to envision that it's traveling through air. There's nothing there. It's just air, but it is something there. There's an atmosphere here. There is not an atmosphere, for example, in space, which is why some sci-fi critics and whatnot get upset when something blows up in space and you hear this loud sound and they're like, well, it's in a vacuum. There's no medium for the sound to be traveling through, so that wouldn't be the case, and so on and so forth. So we have to envision that there's some kind of medium there. That also leads, by the way, to some other concepts that you might have heard of, like scientifically, like the ether, where they said that everything has to have some kind of ether, even if there isn't an atmosphere. There's got to be something because things travel through empty space, like light possibly is still going. Light has to be a wave or a particle, and so on and so forth. And then if you hear these concepts, then of course, once they go out of the scientific realm, you also hear them in like spiritual realms. You hear these kind of concepts that are all this idea that you would think that everything's kind of connected or has to be traveling through something. So there's this tendency to want to say there's got to be something there, a medium that's going to be traveled through. And that basically comes from this concept often of waves that we see water traveling through, that we see the sound traveling through. So requires a source, medium, and receiver. So what do we need to basically define sound? Well, there has to be a disturbance in the force, right? A disturbance in the air molecules in this case by the plucking of a guitar string, for example, which makes the air molecules move, which we can imagine that movement, if we were to visualize it, something like dropping a pebble into a stream, that a completely lake, a nice still lake, the pebble drops in, the waves then are going to be emanating from that. That's what happens from the guitar traveling through the medium of the air. You have to have air so it can travel through if we're talking about sound, right? Light gets a little confusing. When you get to light, is it a particle or a wave? I don't know, it's a little more confusing, but the sound has to go through the air as far as I know, and then it's got to hit something, and that's the receiver, which is usually an eardrum. which leads to the good old question of what if a tree falls in the wood, no one's there to hear it? You don't have that last bit of the definition, someone receiving the wave, and that's why you have the question that leads to the paradox, and you become a Buddhist monk after hearing it because you're like, whoa, dude, like something's crazy with that. So components of the sound wave. You've got the frequency determines the pitch. Now that's going to be, we'll talk a little bit more about that shortly. The pitch is going to be something that helps us to determine the note names. When we talk about music theory, just playing the guitar, we just talk in terms of letters, right? These are the notes that we are playing. How did they define those notes? Well, they come down to frequency. That has implications on how we would expect the music theory to be laid out on the fretboard, as well as just in a theory format, which means that it would most easily be laid out, as we'll see in Excel. Amplitude determines the volume. And then we got the waveform determines the timbre or tone color. We'll talk more about that later in future presentations, and that's the one that could give us some inkling, at least, as to why the formula is the way the formula is, right? So that's the other thing we take a priori. We just say, okay, what's the formula we're using to get our 7 out of 12 notes? Well, we just supply whole, whole, half, whole, 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 half. Well, some of that might be because of the waveform. Now, the other thing that's going to be useful just to understand with that is that different instruments are often determined, you can determine different instruments by basically the color of the instrument. You can say the waveform of it. And you can kind of imagine this like if you were dropping a rock into a pond, it's going to have not just one wave, right? It's going to have like multiple waves. It's going to have like a main wave, you would think, and then a bunch of other little rippler waves that are around it. So that means this was a little bit difficult for like AI music before, because before they got sophisticated with AI music, you would try to simulate the sound by just isolating one wave, one sine wave. But that's not going to sound like any particular instrument. It's too raw. It doesn't sound right. It doesn't sound right to our ear. It's not natural. There's got to be the pebble dropping in. It's not going to have one wave that comes from it. It's going to have multiple waves. So when you look at AI music, which is amazing that they can do right now, they're actually putting together multiple waves that are mirroring the patterns that happen when you drop the pebble of the string on a guitar into the pond of the air. And so they're actually layering multiple different waves, simulating the response, which is quite complex, you would think, to actually do. But the AI, of course, with enough understanding can kind of do that. But you would think they're still going to have it'd still be a little difficult to do weird things like bending strings and tapping or hammer-ons and pull-offs. You can get a bunch of different sounds, particularly from a guitar, by the way you hold the strings down, right? And that's going to change the kind of what you might call the color of it. So in any case, duration, length of the note or sound. All right, so how do we measure frequency? Measured in hertz, cycles per second. So if we envision one wave. Now remember, again, any sound that you hear, unless it's coming from a computer, will not be just one wave, right? It's going to be the disturbance in the force. A pebble in the pond doesn't cause just one wave. It causes a ripple of waves, multiple waves that are happening. But we're going to envision it as one like main wave, right? The main wave that's basically going, and then you can measure how fast it's going, and that's going to give you basically the frequency, which we can measure in hertz and see how many cycles. You can see this just from mathematically, you got to top to bottom. So you can measure the cycles from hump to hump or from the trough to the trough and measure how many cycles are happening and how fast they're going by. And so then we have higher frequencies or higher pitch. So when we're talking about pitch on the guitar, we're typically thinking if I go from the low strings on the guitar to the higher strings, the skinnier ones that are located closer to the floor, you're going to get a higher pitch sound. It's going up sound-wise as we go down towards the floor, or as we go up horizontally on the guitar towards the body of the guitar on one string, the pitch gets higher. That's happening because there's more cycles per second in the sound. So that means technically noticing that when we look at the actual vibrating of the string, when we have a shorter string, which is what is happening when we put our finger down on a fret, then that's going to change the speed of the vibration and whatnot, which is going to change the pitch and so on. So lower frequency has a lower pitch. So the perceived highness or lowness, that's what the pitch is. Pitch perception is logarithmic. Each octave doubles the frequency. Now, this is going to be important to us for a couple different reasons. One is this kind of gets to the idea of how do they name the notes? What do the notes mean? Well, the notes mean that they're actually simply counting the frequencies that are happening of the main wave of the if you drop a rock into the puddle, it's the main wave. That main wave is what we're going to use to define it. The other waves is going to give us the color of it, the littler waves, and that main wave we're gonna measure the frequency, how fast it goes, and then that's going to give us basically we're going to assign a letter to it. Now, is there any reason they assigned an A to what they assigned an A and so on? Not really, as far as I can tell. They just assigned a letter to it because we need to call it something that's a little bit easier than how many times it passed, right? Because that would be like a 3-digit number. We want to give it a 1-digit name, and so that's going to happen. Now, you can also see that the fact that it happens logarithmically, I don't want to get in, obviously you might get, well, what are we getting into calculus here or something? Like, no, we're not going to get into calculus, but just note that what we're saying here is that that there's a pattern. So that means if there's a pattern, that means that the letters that we are assigning to this pattern, to these waveforms, have a pattern that we should be able to see. So if we assign letters to it, 12 letters for the musical alphabet, you would expect those to generate patterns as we make music. Where's the best tool that we can see patterns? Excel, right? A spreadsheet. The spreadsheet, we want to map the things out on the spreadsheet because we expect music to follow a very consistent pattern, of course, right? Because it's just based on now, an A4, for example, is a 440 hertz, and an A5 is 880 hertz, meaning those are going to be the cycles per second. So when we think about the letters that we have assigning to the musical alphabet, we have the letters in the alphabet, A, including sharps through G sharp, right? And then we also have the octaves that are going up as well. And those are just going to go up linearly by this number. Now, again, why did they assign it an A? Well, they didn't want to call it 440, right? We're not going to say, oh, it's a 440, right? And if we did call it a 440, it would be more difficult for us to see the octaves because basically the octaves repeat. So that means that visually, what do we have here? What happens? If we then assign note names to these numbers that are actually happening, these numbers are what are being picked up, for example, when you actually tune your guitar with an electric tuner, they're going to give you this thing, and that's how it knows it's an A and whatnot. So that means that we can see this thing linearly, right? Because it's going to go up, and it just simply goes up by the pitch. So we would expect then that we have a linear system for the notes that we have, and it would keep going up after 12 notes. We can imagine it keeping going up. However, we also note that there's a similarity in the pitch once we get to an octave. So that means that there's the A here is going to sound similar to the A that's going to be an octave up after the 12th note. So that means that I can also envision it in a circle. So these are the same notes in a circle. Here's the A starting here, goes around in a circle. So these, from a practical standpoint, are the two ways that we will typically envision our musical alphabet. And this is going to be very practical because that's the basis on which we see our scales. That's the basis on which that we're going to envision the intervals that we're going to be putting together. Now, notice in actuality, of course, these two ways of envisioning it are a two-dimensional representation. What's really happening is you should be envisioning, if we were more sophisticated, if our mind could envision like in 3D very well, then we would add a dimension and you would have something like this, right? And what would that be? Well, if you looked at this, you'd have still a linear format. There's directionality to it, and it keeps on going forever in theory, just like a number line. But there's also repetition. So you would think at this point, if that was an A, then this would be an A here. So there's going to be some similarity in the sound of the two A's. They're an octave different. So you can see that there is both similarity in a circular format, and there's going to be a distance component to it. This representation over here gives you an idea, like here's the A and here's an A. So obviously linearly, this A went up to here, but you can also see it as a circle where the A, what's an A sharp, I guess, is now basically repeating. Now this image over here was created by AI, so it's not perfect. All the letters aren't perfect. It's just to give you a kind of conceptual understanding. We don't actually envision it this way. Why? Because, I mean, our minds don't work that way. That's too many dimensions for us to envision. So what we end up doing is picking one. We have to say, okay, well, what's my goal? What am I trying to understand here? And based on what I'm trying to understand, would it be better for me to think in a linear fashion so that I can possibly use, for example, math, which is one reason it would be best for us to actually add a number to the notes? Or am I thinking in a way where it would be easier, what my task is, whatever I'm doing, possibly building a chord or something, I don't need to count up linearly past here. I need to see it as a circle because I'm looking for the D. I'm not really worried if it's an octave up, for example. I just want to find the D, the shape that's going to be involved. Now, the same thing happens when we have a two-layered system. Notice that we have 12 notes. So we have 12 notes that we have defined by the pitch that then we can imagine repeat on forever, but they also repeat based on the octaves that we have. And then we pick 7 of those. Now we haven't got into like, why do we pick these 7 notes? It's not always these 7 notes, but it's the pattern is the same. I can use this pattern whole, half, whole step, half, whole, half. As we go back to the C, you can use that pattern based on any note as the starting point, and we just kind of accept that in music theory a priori. We just kind of say, well, that's just the way it is. We haven't really answered any questions why that is yet, but we do see that once we pick 7 notes, you end up with the same phenomenon with directionality or the spiral understanding of the notes we're left with, meaning now we have a scale, which you can call C major and related modes, but it's really just the same thing that you have 7 notes now. So now I have 7 notes out of the 12, which I can think of as just a series of notes in and of themselves in a similar way as we did with the 12 notes over here. We can see them directionality repeating. So if I keep on continuing with this pattern down, I would have a C down here, and I can envision it linearly. And I can also envision these notes circularly, which could be useful when we're trying to, for example, pick up the intervals or pick up a chord shape. Then we're often going to repeat around in a circle, right? And so sometimes on the guitar, for example, we kind of drop the octave idea because we're just trying to grab a shape that fits. And that's hard enough on the guitar. Whereas on the piano, it's a little bit easier to see what's happening because you're on like one string. So you get a lot more into the idea of you're in an octave up or this, and so on and so forth with the different octaves. So, but the true idea is going to be this. So that's going to be the general idea. Now let's take a quick look at an online tuner here. I'm not like advertising for this particular tuner. There's a lot of basically free tuners. There's a lot of app tuners out there. But I just want to note that whatever tuner that you're looking at, you can see the hertz down here, which is of course then going to translate into the letter. So if I was to play like a low A, then we've got the letter, and then we've got the hertz that are calculated. We were looking at this little out of tune. But that's the general idea. So that's going to be basically how obviously the tuner is going to be, calibrated, or how it's basically working. It's counting that out clearly mathematically and then assigning the letter to it, which was assigned somewhat arbitrarily. But now that it's been assigned, we can have an understanding of what that underlying idea means, so that we can hopefully have a better understanding to envision the two ways we can see going up the guitar linearly as well as circularly when we think about octaves, and then also we can linearly and circularly, and then we can imagine that really should be like a spiral type of shape in our mind, which is too complex to really visualize. Therefore, we pick one whenever we're at a particular task, whichever one suits us better, a line or circle.